Hi, everyone. Hello. Hi, thank you so much for coming tonight, or accidentally coming to a talk on quantum gravity. I promise it's going to be super interesting. This is part of a larger series of talks called Curious Conversations, which has recently just been hosted in Santa Barbara, but used to be hosted in San Francisco. It is my absolute pleasure to introduce today's speaker, Molly Kaplan. She is a fourth year, oh yes, let's all clap for Molly. She is a fourth year graduate student in the physics department at UCSB, and she's absolutely brilliant. This is going to be awesome. And the floor is hers.
Oh. Thank you, everyone. Thank you, Mathilde. Okay, so like Mathilde said, I will be talking today about quantum gravity. Thank you all for coming. Thank you, Brass Bear, for hosting this. And yeah, we'll go through a tour of some recent developments in quantum gravity and some open questions. So before we start on our journey, first have to tell you what quantum gravity is. So we have two theories that I'll tell you about in physics that are quite well known. First is the theory of general relativity. This is the theory that describes physics on very large scales, scales of the solar system and the universe. And what this theory tells us is that we can combine space and time into a structure called spacetime, and this structure has a definite notion of distance between 2 points. It can be warped and bent in certain ways. And what general relativity tells us is that massive objects can bend this structure, can bend space-time. And the more massive an object is, the more it bends this structure. So here I have a little cartoon. This mesh is a cartoon of space-time, and you see the sun floating on top of it. It's warping our space-time structure. And then in this little tiny one is Earth. It's also warping space-time, but not quite as much because it is a lot less massive than the sun. Oh. Great. Okay, so we have this theory of general relativity. It's very well tested. We'll talk about one recent development, the detection of gravitational waves, in a second. That's one confirmation of this theory of general relativity. And so this describes physics on large scales. It tells us about gravity, how bodies are attracted to each other, and the physics of these bodies on massive scales. Then on the other side, the physics of the very tiny and small, physics of atoms, electrons, protons, the small scale world. And this is described by the theory of quantum mechanics, or more generally, call it quantum field theory. And you don't really need to know what that is. I'm just going to use this term later. It's essentially just a generalization of quantum mechanics. And all we really need to know about quantum mechanics is that physics acts a little bit differently for the small scale world. There are a few quantum attributes that I'd like to tell you about. So first is the idea of superposition, quantum superposition. And this is well described by the thought experiment of Schrodinger's cat, where you put a cat in a box, you have some quantum system like an atom decaying. If the atom decays, there's a toxin that's released and the cat dies. Or the atom doesn't decay, nothing happens, the cat is still alive. And while it's in this box, we say the cat is in a superposition of both states, both dead and alive. When you open the box, you see either the cat is dead or alive. You make a measurement. So this is what happens in our quantum systems. We have the system, it can be in a superposition of both states at once. When we make a measurement, we know whether it's in one state or the other. Great. So that's superposition, kind of a funky thing that we don't see on our normal classical scale. And then we also have entanglement. Entanglement is this sort of special correlation between two systems. So you can think of two electrons, and if they're highly entangled with each other, if you measure the state of one electron, you know the state of the other. even if they're separated by a vast distance. Great. So these are two of the main quantum attributes that make quantum mechanics very interesting, very different from physics on the scales that we see it in our normal everyday life. Great. So I told you about general relativity, tells us about gravity, quantum mechanics, the physics of the small scale world, and what happens if we combine the two. Well, this is where we get our theory of quantum gravity. It's a theory of everything, tells us about physics on all different scales, from small and tiny to very massive, large-scale physics. And so it's sometimes called the holy grail of physics, being able to find this theory of everything in the universe. And there are different theories of quantum gravity. So we have string theory. I think this is the main one that physicists subscribe to, and it's the community that I'm coming from. There's also loop quantum gravity, and then other types of quantum gravity theories. And one thing to know about quantum gravity is developing a full theory at all energy levels is very, very difficult. String theory includes a lot of intense mathematics, and so we tend to work in certain limits. So either we go to lower energies, or we work in a limit called the semi-classical limit. I'll talk a bit about this later. The idea is that we start with a general relativistic background. We start with a space-time, and then we add small quantum effects to it to understand quantum gravity in this regime that's a little more tractable. Great. So I told you about quantum gravity. It's a reconciliation between general relativity, large-scale physics, quantum mechanics, small-scale physics. But when are these large and small scales ever going to coincide? And the answer is, if it turns back on, yes. The answer is in regions around black holes. Black holes are very massive objects, but they're also places where we expect quantum effects to be important. So we expect there to be some quantum gravity signatures in these areas around black holes. And so they're really important for studying quantum gravity. And it's especially important because we know that black holes happen in our universe. They're astrophysical black holes. So here's a picture from very recently, I think 2019, from the Event Horizon Telescope, the black hole in the galaxy M87. We can also detect black holes in other ways through, this is from the LIGO, the Gravitational Wave Observatory. And you can see these gravitational waves, these ripples in space-time from black holes moving around each other and merging, black holes and neutron stars. So we know that there are these sort of phenomena, these black holes, that possibly have some sort of quantum gravitational effects. And we know they're in our own universe. However, the effects from quantum gravity are quite small. So at the level that we have our experiments now, it's pretty hard to actually detect these quantum gravitational signatures. There has been some news recently. I thought this headline was pretty funny. Physicists create the smallest, crummiest wormhole you can imagine. And basically they used a quantum computer to simulate a system and said that it may be emulating some sort of wormhole. Other physicists said, I don't really know if this is actually happening, but we could be on the verge with quantum computation technology of actually being able to simulate these sorts of exotic structures like black holes and wormholes. So I'll talk a little more later about some potential experimental applications of quantum gravity. But besides that, right now we're not really at a point where we can test this experimentally. And so why do we really do this? And part of it is just out of curiosity. It's out of a legacy of wonder, of wanting to understand the universe at its deepest levels, knowing the mathematical structure behind everything. So that's really what's driving this research. Okay, so now that I've introduced you a bit to quantum gravity, let's jump into our tour through some recent developments. So first, black hole information, and I'll talk a bit about the black hole information paradox, which some of you may have heard of. Great, so we start with our black hole. Black hole, as I said, is a very massive object. It has a horizon, and past this horizon, if something falls in, it cannot escape. It can never get back out. Hawking performed a calculation and saw that this kind of weird effect happens in the vicinity of black holes, where a particle, two particles, will pair produce out of the empty space around a black hole and very quickly annihilate each other. However, very close to the horizon, it's possible for one of these particles to fall into the black hole and the other particle to go outwards. And this becomes a Hawking particle or Hawking radiation. And it'll seem from an observer who's watching from the outside like the black hole is radiating. Because of these quantum effects, the black hole is like a thermodynamic object. It has an entropy, which is just a measurement of disorder. It even has a temperature at this horizon. So that in itself is a pretty cool result coming from Hawking. But we also have a few other consequences of Hawking radiation. The first is that this radiation causes the black hole to lose mass, and eventually it will evaporate totally. It will evaporate fully away. So that's one of the first consequences of Hawking radiation. Another one is in his original calculation, he showed that the radiation contains only macroscopic information about the black hole. So what this means is that the radiation only can tell us about things like the mass, the angular momentum, and the charge of the black hole, and nothing about all of the details going on in the interior of the black hole. So if you take these two consequences of Hawking radiation, you end up with a paradox. So let's say we start with a black hole, it's radiating, and we drop a book past the horizon of the black hole. We wait a really long time until the black hole has evaporated, and then we're just left with this radiation. Now, as I said, it's only containing macroscopic information about this black hole, and so it will only tell us about the charge and the mass and that sort of thing. If we instead change the color of the book, so we drop a different black and white-ish sort of book in the black hole, we go through the same process, we're left with the same pattern of radiation. Because if we drop this book in and keep all of the same macroscopic properties of the black hole, then this radiation pattern will be exactly the same. So this is where the paradox comes in. We seem to have lost some information. At our final state, we have this radiation, and it's the same whether we drop the red book in or the black and white book in. So we don't really know what the color of the book is from our final state, our radiation state. And this contradicts our expectations of what's called unitary evolution. This is just essentially the idea that information is preserved in quantum processes. This is one of the fundamental principles of quantum mechanics, and so physicists really expect it to hold true. So this becomes a paradox, and people, I think for around 50 years, physicists were trying to figure out how to resolve this. And just in 2019, there was a proposed resolution to this problem, and it happens at the semi-classical level, which, if you remember, is just when you add a few quantum effects to your general relativistic background. And this is really exciting. We thought you would maybe need a full theory of quantum gravity to understand what's going on inside of the black hole. So being able to work in just this tractable limit is really exciting. Okay, and the gist of this resolution is that there are some added extra quantum effects that we missed out in the first place. When we add these effects, we actually can encode the radiation, encodes the state of the black hole. So this is really where the key to the resolution is. We end up restoring unitarity because your radiation pattern at the end contains information about your black hole system, contains all the information, not just the macroscopic information. Great, so one way to understand this resolution, I'll just do a overview of the proof, but essentially it's using these mathematical wormholes. And in order to talk about that, I'll start by introducing something called the path integral approach to quantum mechanics. So in quantum mechanics, we write things in this sort of formulation, and all this means is we're trying to understand the probability that a particle will go from point A to point B. And in order to calculate this, we can do it through this path integral approach where we consider all possible paths between point A and point B that this particle could travel. And we take a sum over all those paths, a weighted sum or a weighted integral, in order to get this probability. Okay, so we can apply this to quantum gravity as well. Here, instead of our points A and B, we instead impose certain boundary conditions. And here, things are a little tricky. As I said, this is a mathematical trick. These aren't real, it isn't quite a real calculation that we're doing in our space-time. So what we do is we take our original space-time, we transform it in some way, and we end up with this universe that does have boundaries, unlike our own universe. Okay, so as long as you're still with me, we're going to try to go through this path integral calculation. So we start with our boundary conditions, the analog of these points A and B, and we figure out all possible ways to go between these two boundary conditions. So one way is just to have two separate universes. You have one universe ending on one boundary, another ending on the other boundary. So that's one way to fill in these boundary conditions. The other way is to introduce a wormhole, this connected universe that ends on two different boundaries. Okay, so we get a wormhole in this calculation, and when this loads, great, okay, so we can, we can apply this approach to the calculation I was talking about before. Thank you, Brad. Okay, so we can apply this to our black hole system, where we're trying to understand the information encoded in our black hole. And using this path integral approach, we can either include these wormholes or not. If we don't include these wormholes, we don't get unitarity. We get information loss. If we do include them, we end up restoring unitarity. So this is kind of, as I said, a weird mathematical trick that we're using here, but it's telling us that in this calculation, we need to include these kind of exotic structures, these wormholes. And maybe this is a clue to how we should study wormholes in other contexts, why they could be interesting in other contexts. So, like I said, in the black hole information case, they're a mathematical trick. But in other contexts, we can study real wormholes that are in the space-times that we're interested in. This is something that I'm working on. I'm working on something called the axion wormhole. An axion is a predicted particle that hasn't been found yet. So it's quite exciting that we can look at these wormholes in other sorts of contexts, and they could tell us something about quantum gravity. Something else that's been an active field of research is studying the traversability of wormholes. This has been something, a story that's been unfolding at UCSB, trying to understand whether you can actually travel through a wormhole. Unfortunately, they're not as exciting as we maybe hoped. If you try to go through a wormhole, it turns out to take longer than if you go around. So, not as exciting, but I think it's still cool that we are looking into it. Great. Okay, and there are lots of other questions in this field of black hole information, trying to count black hole microstates in string theory. So this just means trying to understand all the different ways information can be contained inside the black hole. Trying to understand the complexity of wormholes, you can think about the quantum information in the wormhole as a quantum circuit, and then understand the complexity of that circuit. And then we didn't touch at all on this singularity in the black hole, the space where all space and time break down. And that's still really up for debate. No one really knows what's going on there. So that's another big field of research. Okay, now we're going to move on to our next part of the talk, and I think this will go a little faster than the black hole information. So talking about the holographic principle. And this is one of the main tools over the last few decades that physicists have been using to understand quantum gravity. And what it tells us is that in certain cases, a quantum gravitational system in some number of dimensions is dual to or contains the exact same information content as a quantum system in fewer dimensions without any gravity. Okay, this is very abstract. So let's pretend this quantum gravitational system is our own universe. We have 3 spatial dimensions and 1 time dimension, and we have a ton of stuff. We have galaxies, lots of matter, stars, supernova, everything. We have a lot of information in our universe. And what this principle tells us is that it may be possible to condense all of this information down to fit inside a much more simple system. A quantum system in fewer dimensions, maybe 2 + 1 dimensions, without any gravity. So this is really amazing. This is a really great tool because we tend to know a lot more about this system than we do about the quantum gravitational system. And so we can use our knowledge of this to maybe understand something about this much more complicated system. Great. However, the last thing I said, our own universe, it's not quite true. This holographic principle has really only been proven, at least through a string theory derivation, for a certain instance called the anti-de Sitter conformal field theory correspondence, or ADS-CFT. Anti-de Sitter is just a certain type of spacetime, a certain type of gravitational system, and conformal field theory is a quantum field theory with some special symmetries. And just a little more detail about ADS. The big thing is it does not look like our universe. And we can imagine it as this cylinder, time is going upwards, and if we take a slice of it, we get this kind of funky hyperbolic geometry. Great. And we can visualize the ADS-CFT correspondence as using this cylinder. The bulk is the gravitational theory, and the boundary is where our conformal field theory lives. So this is kind of the ADS-CFT correspondence in a nutshell. And there are a lot of ways we can apply ADS-CFT or the holographic principle to try to answer other questions. So for instance, are there other dualities, other places we can apply the holographic principle, maybe that look like our own universe, as I'll talk about in a minute? This tells us there is a correspondence between these two systems, but how does that correspondence work? How do we map information between the two systems? So that's something that's been being actively studied, and especially applying tensor network constructions, if you've heard of tensor networks. So that's a very cool application of them. And lastly, maybe quantum gravity in the lab. Maybe we can simulate these quantum systems and learn something about their gravitational duals. And this goes back to that wormhole, the Prometheus wormhole news article that I mentioned. They're kind of simulating the quantum system and saying maybe we know something about the wormhole in this duality. Okay, great. So the last stop on our journey is our own universe. And like I said, anti-de Sitter does not look like our universe. Instead, it's a different type of space-time called de Sitter that looks a lot more like our universe. And there are 2 reasons that this more accurately represents our cosmos. The first is that we are in a period of accelerated expansion right now in our universe. And we had a period of accelerated expansion called inflation at the very beginning of our universe as well. And both of these are very easy to embed in de Sitter cosmologies and not in other types of spacetime. Great. The other thing is that de Sitter has a horizon in the past that radiates thermally, so gives off this energy. And this looks a lot like our cosmic microwave background. So this is kind of a remnant from the Big Bang. There's a temperature that permeates throughout space, this radiation, and it looks like it can be embedded in de Sitter space. Okay, so in trying to understand quantum gravity in our own universe, maybe we can apply the tools of holography to de Sitter space. So maybe we can find some sort of de Sitter CFT correspondence. And this is fairly difficult. The first is that ADS, remember, was the cylinder, so it has a boundary. Here, there's no boundary in de Sitter, and so there's no place for that quantum field theory to live. And there's also no string theory derivation. ADS-CFT has one, but no one's really been able to come up with something for a de Sitter space. Some models have been put forward. Again, there's no string theory derivation, and they're not really on strong footing as of yet. Okay, so maybe we try something else. We try not using the holographic principle and instead focusing on de Sitter space itself. This is one field of research that's been pretty active recently, and it's a little abstract. It's about understanding a space of observables. And observables are just things that someone could measure in a universe. So we're trying to understand the possibilities for what someone could measure in this universe. Something that's really interesting in de Sitter is that the observer is inside the gravitational system. There's no boundaries, so there's nowhere for all their gravitational energy to go. And so we really have to include the observer in our space of observables. We really have to include them in order to understand the physics going on. And this isn't like quantum mechanics where you can have a quantum system and an observer, and the quantum system can do what it does, and you only care once someone makes a measurement. Here, you really have to include the observer in the description. And this can be made mathematically precise using something called von Neumann algebras. If anyone's heard of those, I just thought I'd mention it. They tell us something about the entanglement structure of these observables, and like I said, they only make sense when we include the observer in our system. So this may tell us something interesting philosophically about the role of observers in these gravitational systems, but it's very interesting mathematically. Okay, great. So finally, for understanding quantum gravity in our own universe, there are many different possible research directions. I talked about maybe some experimental tests, and we're not quite there yet, but it's possible we could have some more precise experimental tests of what's called the string landscape. Essentially, string theory admits many possible solutions for how our universe could look, and maybe we could test some of those once we have precise enough instruments. Or maybe we could do it a little more theoretically, using machine learning for these solutions in string theory. Machine learning is a great candidate for this because the data set of possible string solutions is very, 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 very large. It's 10 to the 272,000 possible solutions at most, I think. So machine learning would be great for sifting through these. We could also potentially have more precise cosmic microwave background measurements to tell us more about quantum gravitational signatures at the beginning of the universe. And lastly, axions are very ubiquitous in string theory in 3+1 dimensions, and so there's a lot of research trying to find these. They could also be a dark matter candidate, so they could tell us more about quantum gravity. Great. Okay, so that is all. Today I talked about quantum gravity. It's a reconciliation between quantum mechanics and general relativity. We talked today about the black hole information paradox and its possible resolution, the holographic principle, especially the ADS-CFT correspondence, and we talked about quantum gravity in our own universe, especially talked a little about how we may play a role in this. Great, so there are many, many open questions. It's maybe possible that in the near-ish future, we could have some experimental applications to answer some of these questions, which would be really exciting. Great. And then the last thing I have here UCSB puts on a wonderful competition, the Art of Science competition, every year. And the slide that I had at the very beginning of these wormholes was my submission last year. And then I submitted one this year called the Dance of the Cutrids. So if you want to go look at all of the entries or vote on them, there's a little code that you can scan here. But otherwise, thank you, and I'll take any questions.